Origin of Earth and Life, Part 2. According to current theory, what we think is going on at this time scientifically, a period of inflation occurred between 10 to the minus 33rd and 10 to the minus 32nd seconds, during which time the radius of the universe grew from 10 to the minus 33rd light seconds, or 3 times 10 to the minus 25th meters, to about 10 centimeters in size. The increase in radius from essentially 0 to 10 centimeters and 9 times 10 to the minus 33rd seconds resulted in a speed of radial expansion of 10 to the 32nd meters per second. This is 3 times 10 to the 23rd times faster than the speed of light. So what's the big deal? Well, why is that an issue? We're moving many, 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 many times faster than the speed of light. Problem? Yes. Relativity was not violated because inflation did not involve transmission of signals or information, only an increase in space. So the universe became puffed at this time. Puffed from essentially a size of 0 to about the size of a football or soccer ball. Why is this special? Why does this matter? Why am I talking about it in this abandoned room in my house? Well, we go from the Big Bang at time 0 to inflation. Now, because our physical constants aren't functional yet under these conditions, these weird conditions at the beginning of time, we are a bit looser in our constraints on how matter and energy behave. Okay, so early on here, we have the inflation period. So we're adding space, but we're not moving anything. If we were to move something, that would generate some physical issues for us. So we're not moving, we're merely expanding. After a microsecond, photons form. After about a tenth of a second, nuclear fusion begins. After 3 minutes, nuclear fusion ends. So we've created matter now, and our cosmic microwave background radiation is emitted at this point. Shortly after this, neutral hydrogen forms at about 387,000 years after the beginning of time. Now, it's thought that gravitational waves arise from cosmic inflation, the faster-than-light expansion just after the Big Bang. This is a different issue for a different course, but it's good to know that this is where this gravitational wave theory comes from, how these waves are generated. Okay, back to some math. The greatest distance at which a point inside a 10 centimeter sphere could see would be 3 times 10 to the minus 24th meters, the maximum distance that light could travel within the 10 to the minus 32nd seconds since the beginning. The volume of a spherule with a radius of 3 times 10 to the minus 24th meters is 1.1 times 10 to the minus 70th meters cubed, while the volume of the 10 centimeter sphere is 4.2 times 10 to the minus 3rd meters squared. The sphere, therefore, contains 4.2 times 10 to the minus 3rd divided by 1.1 times 10 to the minus 70th, or 3.8 times 10 to the 67th spherules. This number, 3.8 times 10 to the 67th spherules, is important. You should remember this number because you're going to need it later on. 3.8 times 10 to the 67th spherules. Learn it, know it, love it. Don't run away just yet. This is going to make sense. At least, I really hope it's going to make sense. According to inflation theory, the larger sphere and all the spherules inside it have since expanded until our spherule has reached its present radius of 3.77 billion light years. All the other spherules have also expanded and become universes of their own, within which objects are in mutual visible contact. This means that our universe is only one of 3.8 times 10 to the 67th other universes that we will never be able to see or know anything about because they started out too far apart from us within the original sphere for their light to ever reach us. So they're out there. This many universes are out there, but we will never see them. We'll never know anything about them because they're too far away. It's kind of sad. As the story goes, after 10 to the minus 32nd seconds, the inflated universe resumes its expansion at the rate given by the Hubble constant. Hubble was an astronomer about 100 years ago, and he discovered what's known as redshift, When things are moving away from you, they appear reddish. When they're moving towards you, they appear bluish. This is usually demonstrated by the sound of a train coming towards you, or the sound of a tractor trailer coming towards you blowing its horn versus moving away from you blowing its horn. The sound waves are stretched out. The wavelength is increasing. So when things move away, they shift red. When they move toward you, they shift blue. Sounds get higher pitch when they come toward you, lower pitch when they move away from you. So why do we need all this complicated multi-universe stuff? It's just ruining your life right now, I'm guessing. Well, it turns out that we need this multi-universe complicated stuff to explain what we observe. The spectrum of microwave radiation pervades the universe today is the same in all directions. This implies that the earliest universe had the same temperature everywhere. Distant regions of the universe whose light is just now reaching us have been cut off from each other since the beginning of time. Because the universe started expanding immediately at time equals 0, there was no time to reach thermal equilibrium. The inflation model says that between t equals 0 and t equals 10 to the minus 35th seconds, the universe was small enough for light to reach across it and ensure thermal equilibrium. Each of the little spheres, the 3.8 times 10 to the 67th spheres, were small enough at that time for energy to be evenly distributed throughout those spheres. This results in number 2. The average amount of matter in space is the same everywhere on a large enough scale, and our scale is 1 billion cubic light years, but is irregularly distributed on a smaller scale. And the result is stars form, galaxies, galactic clusters, and filaments result from the tiny irregularities. The thermal equilibrium across the earliest universe suggests that radiation density was also uniform, except for the exceedingly minute random fluctuations. And those are important for generating these objects. As a result, when matter condensed out of this radiation, its distribution on a large scale in space was also uniform. The minute random density fluctuations were magnified by inflation to form small-scale fluctuations in the density of matter, which resulted in the accumulation of stars and galaxies. In this standard model, magnification would have been too slow to account for the stars and the galaxies that we see around us. Number 3, certain massive particles called monopoles seem to be missing. Monopoles are massive particles consisting of individual north or south magnetic poles. According to theory, monopoles should have formed in great numbers in the early universe, but they are not observed today, even though they should be readily detectable because of their large mass. The inflation model says there should be as many as 10 to the 67th different universes, such that one universe may contain only a few monopoles. This would make their discovery very difficult, if not impossible. So maybe they are out there around us. There aren't many of them. They're far, far away. They're very massive, but we haven't found them yet. Number 4, flatness of the universe. The average density of matter in the universe, 0.9 times 10 to the minus 30th grams per centimeter cubed, is really close to the limit between an open universe that expands forever and a closed universe which stops expanding and may collapse kind of universe. The early universe was ultra-dense, and therefore its space-time would be highly curved. The enormous inflation that took place flattened out space-time just like a balloon flattens out its surface as a balloon is inflated. When a balloon becomes very, very large, say the size of the Earth, you could not tell that that balloon surface is curved. This brings the average density of the universe close to the critical value. The universe contains matter and not just radiation. Between the end of the Planckian and inflation, matter and antimatter briefly appeared but were unstable at those high temperatures. When the universe inflated, temperatures dropped, and energy was converted into both matter and antimatter, which could now remain stable. Matter and antimatter readily change into each other, but the reaction of antimatter to matter is slightly favored. The calculation is that 10 to the 9th plus 1 quarks were created for every 10 to the 9th antiquarks. Quarks and antiquarks did not stabilize until time was equal to 5 times 10 to the minus 6 seconds when the temperature dropped below 3 times 10 to the 12th kelvins. At that time, nearly all matter and antimatter had been converted back to radiation, with only one particle in a billion surviving this interaction. And this explains the observation that the ratio of matter to photons in the visible universe is 1 to 10 to the ninth. The matter that survived forms all the objects we can see in the universe. When the temperature drops below 10 to the 12th Kelvin, deuterium becomes stable, and at 10 to the 10th Kelvin, helium-3 and helium-4 nuclei and their electrons become stable. And this was the end of matter formation, because the next in line, helium-5, is very, very unstable. It has a half-life of, I think, 7.6 times 10 to the minus 22nd seconds, which is a very, very tiny amount of time, essentially instantaneous. This model is a result of calculations rather than guesswork, and as a result, it matches our observations, where we see 74% of matter in the universe being hydrogen and 26% helium. That's within stars and interstellar material. Electrons are free to roam about. The universe looked kind of like a luminous fog, much like a sign, an argon or neon sign. And the temperature eventually decreases to about 3,000 Kelvin at 380,000 years after the Big Bang. Now the energy is low enough that atoms become stable as atoms. We can see that here in this diagram. We go from inflation to the afterglow light pattern. This is the neon glow, the plasma glow that we were just talking about. Once that clears up, now that the universe is clear, we enter what's called the dark ages. At this time, the electrons have been captured and the universe is now transparent. There's nothing to see because density had decreased to 1.6 times 10 to the minus 17th grams per centimeter cubed, and there were no stars yet. It was darkness throughout 3.8 times 10 to the 67 universes. Again, we can look back in time by staring out into space. This is the Chandra Ultra Deep Field we mentioned before. This represents the universe at about 800 to 900 million years after the Big Bang. Many of the things you see in this image are much younger than that. It's only the very faint, dark, reddish specks here that represent the universe at 800 to 950 million years. We have things to do yet, ideas to test, but we're pretty confident that the observations we have made, particularly in the last 20 or 30 years, match the predictions by physicists. Additionally, this is spelled wrong, the Titius-Bode law, which states that planetary distances from the central body are not random, it indicates that a planet like Earth is likely to exist in most, if not all, planetary systems. This law isn't perfect. In fact, it's not all that good. It essentially states that each subsequent planet is going to be about double the distance of the previous planet from the central orbiting body. Neptune posed a big problem, and Mercury poses a bit of a problem. So in reality, it's kind of a good idea, but it doesn't quite hold up because of a lot of other complicating factors. Now, keeping this in mind, calculations suggest it is probable that there are 0.8 times 10 to the 21st planets like Earth in the visible universe. That's in our universe. Now, if you multiply that by 3.8 times 10 to the 67th, that's a whole lot more planets out there. The average age of a star like the Sun in the visible universe is probably similar to our Sun, about 5 billion years. For argument's sake, we'll say the human brain achieved its present size about 125,000 years ago. Most likely it was more like 250,000 years ago. Assuming that Homo sapiens will soon be extinct, maybe sooner than we thought as of last year, the average window for intelligent life is 125,000 years divided by 5 billion years equals 2.5 times 10 to the minus fifth. Assuming that each planet has the same population as Earth, and this isn't quite accurate anymore, we'll say 7 billion people. The number of people in the visible universe is 0.8 times 10 to the 21st times 7 times 10 to the ninth times 2.5 times 10 to the minus fifth. That equals 1.4 times 10 to the 26th. Now, because there are 3.8 times 10 to the 67 universes, the total number of people might be 7.4 times 10 to the 93rd. This is 7.4 followed by 93 zeros, which is a lot of people. Now we're going to talk about stars for a few minutes. The sun and other common stars produce energy by two processes: proton-proton chain and the carbon cycle. Here we have an illustration of proton-proton chain reactions. We have two hydrogens coming together here. They're going to kick off one particle and now form a deuterium. This deuterium, which is a hydrogen atom with a proton and a neutron, is going to collide with another hydrogen, kick off some radioactivity, and generate a helium-3 atom. When two helium-3 atoms come together, they're going to kick off two hydrogens and form a helium-4. The proton-proton chain requires a temperature of 15 times 10 to the 6th Kelvin to take place. So this is why it doesn't happen in empty space. It happens in the center of stars. The carbon cycle requires an even higher temperature because it takes more energy to run a proton into a carbon nucleus, which contains 6 protons, than attach it to another proton. In our sun, about 91% of the energy is produced by the proton-proton chain and the rest by the carbon cycle. Stars that are bigger than ours have higher core temperatures and produce energy mainly using the carbon cycle because of these higher temperatures and higher pressures. These stars are initially formed when a diffuse cold gas cloud gets shocked into collapsing by a passing shock wave, usually caused by a supernova like the Crab Nebula. When a cloud collapses, heat is going to be generated as that matter contracts inward, and the shrinking cloud begins to rotate faster and faster in order to conserve angular momentum, which brings us back to our ice skating model. The skater pulls his or her arms in, and their rotation speed increases. The rapid rotation forces some of the material of the original cloud to form a disk rotating around a central body. And we can see that here. We have a giant cloud of gas. It's beginning to clump together after its shocking experience. And eventually, these cores of material are going to form larger and larger clumps that are ultimately going to become stars with a rotating gas disk around them. Eventually, this gas disk is going to become more organized into planets. Now, when we look into the future, when the temperature reaches 10 to the 7th Kelvin, the proton-proton chain starts and the star is born. The spark has been lit and the barbecue is ready to go. However, as hydrogen is used up, the star shrinks and heats up. A middle-sized star like our sun, we're just average out there, will heat up from 15 to 100 million kelvins. The energy buildup is way too fast for the heat to be radiated away, and the star puffs up in response, like a popcorn kernel. In fact, it's expected to expand by 100-fold. In the case of our sun, the surface will reach between Mercury and Venus, which we can see here. Our current sun, 4.6 billion years old, is going to expand. And as it expands pretty rapidly, it's going to bloat out and absorb Mercury and Venus, ultimately reaching the Earth and burning away our atmosphere and our oceans and slowing our orbit down until we are plunged into the center of the sun. Meanwhile, real estate gets valuable out here in Jupiter and Saturn. Now, the planets themselves aren't ever likely to be suitable for life as we know it, but some of their moons are. Jupiter has a number of large moons that you can see with a cheap pair of binoculars on any given night. Saturn likewise has a very large moon named Triton, which already has an atmosphere and an ocean, so it might be the place to be. But now for some bad news. Luminosity increases, but the temperature decreases to about 3,000 Kelvin. Our sun has now become a red giant.